I have some writing on here. I hope that's okay. I just did another video, but it was taking way too long, and so I don't want to erase all this and then start again. I already erased some of it, but I'm gonna try and go a little bit quicker because I was already at about 15 minutes and I had just gotten to the gates for the transport. But homeostasis. So we have homeostasis up here. Basically, what homeostasis means is that your body is in like optimal conditions. Um, you can achieve homeostasis or you can have homeostasis whenever there's a variable. And we have numerous variables that your body comes in contact with and is like, okay, I want to be in a specific way, in a specific range. And if I am in that range, I am happy. And when your body is happy, your body is in homeostasis. An example of how it might work in the body, this is the one I had. So let's say 98.6 degrees, that's your set point right here in the middle. And we're up here, we're really hot. We're at about 101 degrees Fahrenheit, maybe more. And so your body's like, holy cow, we're hot. We want to go a little bit lower. What can we do? So what your body decides to do is it will take blood, it will dilate your blood vessels, try to get some of that heat away, but it'll also activate sweat glands. That way your body will sweat. In that water, heat will be dissipated as it evaporates, as the sweat evaporates. And so your body wants to then come back down to the set point at 98.6 degrees Fahrenheit, or at least in the acceptable range. I don't know if it's like a degree or so, either way. And then it'll be happy. And then it won't have to sweat anymore. So the components of a reflex control pathway for that, reflex control pathway, we have a stimulus, we're really hot. The skin feels it, that's our receptors. It sends that information along the afferent pathway to the control center, which most of the time is the brain. The brain then takes that information and is like, okay, I need to figure out a way to fix this problem. So then it sends information on how to fix the problem through the efferent pathway to the effectors, and the effectors are going to be the ones that fix the problem. The control centers are the ones that come up with the idea, but the effectors actually do the job to fix it. In this case, it's going to be the sweat glands, which then cool the body off, or the blood vessels in dilating. I'm sorry, I have a cough, so if I cough a lot, I'm sorry. Negative positive feedback loops. So this one is a negative feedback because the definition of a negative feedback loop is we want to come back to set point. If we are coming back to set point, a stimulus is causing, or something is causing us to go away, the heat, being outside, whatever, the heat is causing us to go away, we want to come back down to set point. So since we're going away from what has been happening, and we're going back down to set point, that's a negative feedback loop. An example of that would be what we just said about sweating. Being outside, it's really hot, your body wants to cool off, you start to sweat, you cool off. Eventually there'll come a point where you come back down to 98.6 or somewhere in that range, and your body's like, I don't need to sweat anymore. That's why when we're inside classrooms like this, we're not all sweating, because we're in an optimal range. We might be shivering a little bit like I am right now because I'm a little cold, but that's just your body's way of trying to come back up to an acceptable range to achieve homeostasis. Down here I have a positive feedback loop. You have an injury, it hits a receptor, your body then sends that information along to the control pathway, and your brain's like, oh my gosh, I have a cut. So what I'm going to do is send information to these platelets, and I'm going to tell these platelets to go to the injury, and I'm going to tell them to release a chemical as they try to clog the blood. And then those chemicals will then attract more platelets, which then platelets release a chemical which attracts more platelets as the platelets are doing their job. Then new platelets come in, those platelets do their job, attract more platelets come by, and so it just constantly compounds on itself too. So in that case, like the loop would be the number of platelets. And so over time in the loop, you're just getting more and more and more and more platelets, as opposed to this, the sweating example. You're probably sweating, I would assume, to say like the most at more the beginning of the cycle, And then as your body starts to cool down, it realizes it doesn't need to sweat so much. It doesn't need to do this process as strongly since we're coming back down. So that's positive and negative. So part 2, describe the 3 types of protein transport. Okay, this is why I have to green out for these. So we have channel, carrier, and what was it again? Primary? No, sorry, active. So we have channel, carrier, and active. Why did I put another A there? I don't know why. Active, which has both primary and secondary. So for channel we have 3 different channels. We'll have voltage gated, which basically depends on the electrochemical gradient. It basically is dependent on the voltage or the charge of the ions or molecules that are going through it. We have this one, which I still don't know how to say, ligand, I think. So this one is going to be specific molecules or substances will bind to specific receptor like ports on the actual gate itself. And then we have mechanically. Mechanically is going to be more like it'll be more sensitive to like touch, pressure, changes in temperature. Those things will mechanically move this channel. Carrier. Carrier proteins, so they bind to specific like solutes. So I can't really. Do I have space to draw it? Can we see over here? We can. Okay, sweet. Put this down. So if we have a membrane, and then right in the middle here we have a specific opening. It sort of is like a revolving door in the sense that it is open right now, and it's not open to, some molecules, and it's not open to other molecules, but it will be open to like specific shaped molecules, or specific molecules. These ones will come in, and when they get in, it'll sort of like revolving door. It'll work like a revolving door, in the sense that once it's in, now it's taking up place, and it's going to start hinging. So it's open here, and as it comes in, it starts to open up the other way. And so now it's closed from the top, from the outside of the cell, and now this substance can go inside the cell. So that's carrier, which I'm just going to check off because we did. And so active, we have 2 different kinds, primary and secondary. The easiest way to tell the difference between the 2 of them is primary active transport needs ATP and energy to actually function, to do its job. A good example of that is going to be the sodium potassium ATPase pump. This thing uses sodium and potassium. It'll pump out sodium, and it'll take in potassium. But it uses ATP at the same time. This is pushing both of them across a gradient. That's why it needs ATP. Because sodium really doesn't want to leave the cell due to the concentration, and potassium doesn't really want to come into the cell because of the concentration. But with the use of ATP, our body and the cells have that, and the pump is able to work that way, and it does it. Secondary doesn't directly use ATP, but it's sort of like a bifactor of primary, hence the term secondary. And so for this, it'll then use things that sort of work across an electrochemical like gradient. So, like if sodium, so we're kicking sodium out, and so sodium wants to come back in, and so if we have let me see if I can bring this. There we are. So if we have like a cell, And so this is going to be the membrane of the cell. If we have, let's say, sodium, and there's not a whole lot of it outside the cell, or actually, let's just use a different, just for an example. Let's use, I don't know, calcium. Does that work? Because there's not a whole lot of calcium in the cell, so yeah. So there's a lot more of a concentration of calcium outside of the cell than there is inside. So due to the concentration gradient, calcium is going to want to come into the cell. But with that, it could then push something else along with it down into the cell. Even though, let's say it's like glucose. Even though glucose might have a higher concentration down here than it does here, it will still find its way into the cell because this is making its way in, which in turn, secondarily, it might have some areas in the channels or that the glucose can then bind to or make its way in. That way it comes in as well as the calcium. So that's going to be secondary. It was a little confusing for me at first to sort of try to wrap my head around it, because I was like, well, if it doesn't use ATP, then can't it just be like simple diffusion, you know? Because it's technically going against the gradient, but it's also going with the gradient. So it's a little bit of a mix of both. It was a little tricky for me, but yeah. And now, so the concepts of specificity, rates, energy sources. All right, slow this down. Let me use another color here. Let's use red. So you have specificity. That basically just means specific molecules for specific channels. You're not going to be using a calcium ion in a sodium potassium pump. That's just not going to work. That won't happen. It's specifically designed for these. So specificity, specific ions, chemicals, molecules for specific like pumps or functions, whatnot. Rates, so rate, it's the rate of like diffusion or transport. Those are dependent on like, it's basically the speed at which it goes, the speed at which the transport or the diffusion takes place. And that's normally dependent on the concentration, also dependent on like the number of like molecules or the ions or whatever you're trying to do. So I guess that's concentration. But like the number of proteins, there we are. So we can't transport a whole lot. Our rate's going to be really low if we only have one protein that's working on a cell to move something in. But if we have, you know, like however many that is, 8. If we have 8, the rate's going to be 8 times as fast, hypothetically, as if just one was working. What else am I missing? Right, energy sources. Energy sources. So that's going to be like ATP is an energy source for transportation, diffusion. The concentration gradient can be an energy source that pushes something along. Also the electrochemical gradient. That's not concentration gradient. I'm running out of space. There we are. Competition. That's sort of straightforward. Things are competing for a specific spot. So like if you have 2 ions that are trying to make their way in, but they're both going to be competing. Normally the one that wins out is the one that has a lot more moles of it out rather than in. So the concentration of this one is outweighing molecule B by so much that more of it's just going to want to come in. They're just competing to make their way in. Competing. I can spell. Saturation. So if we have way too many ions, so we have so many ions, but we have too little proteins. It doesn't matter how many more ions we put in here, or we have. We don't have enough proteins. The rate of transportation or the rate of diffusion is going to just stay the same because it's so saturated that there's too many molecules, ions to be then for the amount of proteins that are going to be able to take those and actually move them. And then direction. Direction, that one's pretty straightforward as well. It basically just means, is a substance going in the cell or is it going out of the cell? Because I want to say all, but I know from this class that I've learned that there are exceptions to the rule. And so I don't want to say it in good faith, but I want to say that almost all, like gates or channels, whatnot, they almost always work in specific directions. You're going to have a potassium-sodium pump, and it's going to be wanting to send them in specific ways. It's not going to be doing it the other way around. So it basically just means the direction at which the substance, whether it be an ion, molecule, whatnot, the direction of it either going in the cell or out of the cell. And I think that was everything. So yeah, thanks. Alrighty, so osmosis. So the process of osmosis, basically what osmosis is it's the diffusion of water. So if we have, let's say like a jug, oh, this is a terrible marker. If we have a jug here, and we fill it up with water, and we have a permeable membrane right here. And we have water up here, and it's just like that. And in we put, some potassium. Over here, we have potassium. We have a lot more. We also have chlorine, or chloride. Chlorine, sorry. Chlorine. So we got like 2 potassium here, and let's say we just have 6 potassium here, and also 6 chlorine. So osmosis basically means that it's the diffusion of water. But the thing about osmosis is it goes from low solutes to high solutes. So if this membrane allows water to pass through, and we have this much solute and this much solute, so we have 2 here and like 12 over here, then more water is going to go from this area of low solute, which is, I think they call it also high water potential. It'll go from low to high. So pretty soon, or throughout the process, this will be a rough drawing of it, but we'll have the membrane here in the middle, and we'll have lower water here and higher water up here because of osmosis. So how does osmolarity differ from molarity? So osmolarity and molarity are pretty similar. Osmolarity really just cares about particles in general. Molarity cares about the molecules of the particle. So if you had like 1 mole of NaCl, it would be 1 molar, but it would be 2 osmolar because there's 2 molecules in the particle. So for glucose, on the other hand, glucose would be 1 mole glucose and also 1
osmol glucose. This looks like I'm putting grams, but I mean glucose. So osmolarity differs from molarity because osmolarity is caring about the molecules and the particles, or in the particles, or the molecules of the particles, while molarity just cares about the particles. Explain how osmolarity and tonicity differ. How can a solution be isoosmotic yet be hypotonic to a cell? Let's go purple, because it looks like purple is actually good. So, isoosmotic yet hypotonic. So, hypo or isoosmotic, yet it's also hypotonic. So if we have a cell, we put it in a solution. So this cell has, 300 milliosmol. And the solution in here is 300 milliosmol. So this is going to be isoosmotic because they're both the same. But if this solution is 5% dextrose, for example, dextrose is going to make its way into the cell. And then at that point, there are less particles in the solution than there are in the cell. Because now the cell is going to have a lot more particles. And because it has more particles, more water is going to want to go to where the more particles are. So water is going to rush into the cell, meaning the solution has less particles as opposed to the cell. And so there's also going to be less water, meaning this is also going to be a hypotonic solution compared to the cell. In part 2, explain how the resting membrane potential RMP of the cell membrane is established. So the RMP is based on two things. And it's going to be based on two things that go in opposite directions for the most, well, not for the most part, but we're going to look at concentration gradient and also the electrical gradient. Basically, the RMP, the resting membrane potential, is based, or is, found when both of these two hit equilibrium. Which they're not going to reach, I think, a true equilibrium, if I remember correctly. They're both going to sort of happen at the same time, but when one gives, one will take. And so we may not be completely separate, but they're just going to be sort of bouncing like this, and so they'll be at equilibrium. And so that's what we call resting membrane potential. What properties, characteristics of the cell membrane account for the RMP's development? So the gradients, especially, these are huge. These are very important on its development. But also, one of the things that matters with the cell is going to be the channels that it has. If it has one channel, then it's not going to be able to develop really well. The concentration gradient is really, really, really high. And the electrical gradient might be really, really high too in the other way. And so now they're fighting, both of them trying to come, one go down and the other go up. And it might take a while. And so that has an effect on its development. What conditions and factors affect the resting membrane potential's magnitude? Okay, so the channels. If we have one that's working, it's not going to be able to do a whole lot of work. It will be able to do this, and I believe it will. I don't know if one channel could actually do all the work for the cell. It might get completely saturated and just not be able to do much really and keep up. But if you have a lot of different channels, then you have a lot of different ways for this cell to hit that equilibrium. And so the size of its potential is going to increase. The magnitude of it is going to increase because you have so many different areas that can affect the resting membrane potential. Another thing would be the delta of these gradients, or the size of the gradients themselves. If one is really massive and the other one is really, really low, the delta of that is going to be very big. And so to come somewhere in the middle, that's going to be a lot more than if we had a graph where, it was right here and right here, trying to come up and reach each other, meet each other in the middle. That's a terrible arrow. Then, this is your electric and this is your molecular or concentration gradient. It doesn't have much. They're only going, like this far in either way. The magnitude is much less than. Oh, can you see that from it? You can. Magnitude's going to be much less. And lastly, a discussion about the Nernst equation and driving force. I'm going to erase right here really quick. I don't like how this black marker is still showing up on the board. I don't know if you can see it. Okay. But so driving force is going to be dF equals Vm minus EP or mv? No, Ex. That was it, Ex. So basically what this is saying is the driving force for an ion is equal to the voltage of the membrane, which most of the time is like -70, and then minus the membrane, or the equilibrium potential. What that means is you'll be given Ex. I'm pretty sure that's what Brother Hunt and Brother Shaw said. I don't think we need to memorize them, but we probably will over the course of the semester. But we'll be given the Ex if we ever need to do calculations. So like sodium's, I think, is like 60. I think it's 65. And it's a positive 65? No, I think it's a negative 65. I don't remember. Oh my goodness, I'm so sorry. Anyways, whatever it is, I think we'll just do negative for now. But you'll take the voltage of the membrane, which is -70, and you're going to minus it by the equilibrium potential of the ion itself. So if we have 65, so for sodium, that means we have -70 minus 65, which is, adding another negative. We have -135 for sodium. And so that's always in the cell. So in the cell, we have 135 for sodium. It's the driving force. Now sodium outside is a positive cell. And since we have a negative driving force, it's going to want to come into the cell. If this was, if we had the same number, same -135, but we had chlorine instead, it would not want to go into the cell because it's a negative ion. Or it's an anion rather than a cation, sorry. It has a negative charge, so it doesn't want a negative number. Now, if chlorine had positive 135, then chlorine would want to get into the cell. So that's driving force. What was the other thing? Nernst equation. So the Nernst equation, can you see over here? Yes, you can. Okay. So the Nernst equation is going to be equals -61.5 over Z log in over out. And these are going to be concentrations, so we're going to have brackets. So basically for this, what we're going to do is we're trying to find for a specific ion. We're going to try and find for a specific ion. So let's take calcium, for example. Calcium, which has 2 valence charges. Calcium, we would then take and we would do, okay, so -61.5 over 2, because Z is equal to the valence charge of the ion, and calcium has 2. And then we would multiply that by the log of the concentration of calcium inside the cell and outside the cell, both of which I do not have numbers for because I would need a problem. But basically, that's how it works. And that's the Nernst equation. And I think I went over everything. Let me just run through osmosis. Yeah. Perfect. All right. That was essay question number 2. Alrighty, let us click over here. Alrighty. So action potential. So I have part of it just up here because I didn't want to erase everything because there's a lot to go into and I feel like it's going to get very messy if I erase it and have to redo it again. But basically an action potential is there's a stimulus that occurs and it causes a little bit of depolarization in the cell, which then, as it crosses threshold, will initiate an action. So there will be a response once it crosses threshold, which is this line right here. Once it crosses that, a response actually happens, and there will be a rapid depolarization of the cell. And then it will start falling, and it will be repolarizing the cell. It will dip down a little bit, do a little bit of hyperpolarization, and then eventually reach resting membrane potential again. The events that would take place. So for the events, something like this, for 1, this area right here, 1, this would be some sodium channels are opening. And then once enough happen, or once enough open and there's enough depolarization that the cell crosses threshold, it will then open all of them and it will just shoot up. And then it will get to a point where all of the channels are starting to close. And that would be right here, which I erased, which would be 3. All of them are closing and now potassium channels are opening. And so now the cell is repolarizing and it's coming back down. And then in 4, over here, this side, the potassium channels are going to be closing and then the cell is going to get back into resting, its resting phase. I have it right here, the rising period is going to be as soon as it starts going up. This will be the rising period, and then as it starts falling, that'll be the falling period. The cell could even just go down like that too, and that is hyperpolarization. But for the most part, it'll be doing stuff like this. We have graded potentials, which are going to be anywhere where there's going to be small changes in the action, well, not the action potential, small changes in the polarization of the cell before it reaches threshold. Once it reaches threshold, then it's no longer a graded potential, it's going to be part of this whole thing, which is an action potential. I think I'm missing some, I think the periods are part of there. Are they? Yeah, relative and absolute. So once we cross threshold, we are in the absolute refractory period, where we cannot have an action potential again because we're technically in the middle of one. Once we cross back down under threshold, we're going to be in something called a relative refractory period, where we can achieve an action potential in this time. It's just going to need or require a much stronger stimulus than the initial one. But eventually it will bottom out again and it will go back to resting membrane potential, and then you can just use a stimulus that's as strong as the initial one was. I think that does it for this. So let's see, we have next, for each phase, describe the actions. I already did that for the channels as well. Compare and contrast graded and action, I did. Give an explanation of capacitance, time constant, and length constant. So capacitance is going to be, you can see over here, let me see if I can move this over. I have a few things drawn, just so I didn't have to erase everything, but, so capacitance is just going to be, it's going to be your charges per your volts. So basically what that means is, we're at negative 70 millivolts. How many charges do we actually have in there in the cell? Can you see? You can. So are we going to be having a whole lot of, positive charges? This is pretty messy, but you see what I mean. Are we going to have a whole lot of these charges? Imagine these are all pluses too. Or are we going to have one like this where we're just we only have a couple. This is very different in capacitance. This is going to be very high. This is going to be very low. Time constant. So time constant is, I forgot the symbol for time constant. I think it's like I think in the book, it's like an R. But it's basically the capacitance of the membrane times the resistance of the membrane. And so what this is basically saying is, how long is it going to take for a signal to get to where it needs to go? If we have a lot of charges, that is going to influence how long it'll take. If we have a lot of resistance inside, that's going to influence how long it's going to take. And length constant is another thing. That's lambda equals the square root of Rm over Ri. Basically, this is saying, membranes, they have, or not membranes, but neurons, they have length to it. And so just like if you have a very powerful signal that's going off, that's fine and that's great. But if the neuron is too long for the signal, it's not going to reach anywhere. But if you had this same neuron or the same signal in strength, but you only had something that was like half as far or half as long, the length constant is going to be down, which means you're going to be able to achieve that action potential, or the signal is going to be able to go to where it needs to be because of the action potential that caused it. Describe the structure of the chemical synapse and explain how signals pass. All right, let's move this further down. Can we see? Okay, so this is a rough drawing. This is what I saw for the Shaw draw. And in the book, it's different. And on Google, they're sort of more like bulbous. They're sort of like this. Which honestly, I think this makes more sense in my head. But I'm just believing that Brother Shaw and Brother Hunt know exactly what they're teaching us. So I'm going to go with this. But we have the pre-synaptic terminal, and then we have the post on this side, synaptic terminal. And then right here, I read somewhere, oh, that was terrible. This area right here in the middle, why can't I do this? There we go. It was, I think, called like the synaptic cleft, synaptic cleft, or cleft, one of the two, maybe minus the T. Anyways, basically this is the end of one neuron, this is space in between, this is the beginning of another. Explain how signals, okay, so you'll have a signal, an action potential will happen. We're going to flood in with potassium, and we're going to have all these charges now. These charges on this neuron over here are going to send the Boang out. Now the Boang is going to reach all the way over here to where we're going to have calcium. I don't want to overwrite green, but there's a gate here for calcium. Calcium is going to come in, and it's going to hit these vesicles. Now these things all have neurotransmitters in them. These vesicles are going to get activated by the signal. Well, the gate got activated by the Boang. I think I said that. Calcium comes in, hits these vesicles. Now these vesicles with the calcium are going to bind to the plasma membrane, or the membrane of the neuron. And it's basically going to tie itself into it and then merge with it and basically release those neurotransmitters. And these are going to be released, and then we're going to have different, these are supposed to be a lot smaller. Let's just do that. These are going to have different channels or receptors, and they can do one of two things. They can either be excitatory or inhibitory. If they're excitatory, the transmitter is going to come to the receptor. The receptor is going to allow more of a charge to come in, and then that will also be able to probably help with the an action potential here to push this off, because like repels like, and so this will push these, which is in turn going to push them even further, and that will just increase the Buang as this goes down, that neuron. Or it could be inhibitory, in which now we're having a negative charge, or maybe just more of like a decrease in positive charges. Regardless, if we have like a negative charge, let's go with that, these negative charges here are going to pull on some of this positive charge. And so instead of having, if we're just using these as measurements, instead of having like 6 lines, and now we have some positive charges, we could have instead, like 3 or 2. And now this Buang, which if it's the same size neuron as this one is, this one needed, 5 Buang lines. This is very layman's terms right now, but this had 5 Buang lines, and it was able to reach here and cause the neurotransmitters to reach. Now this one only has 2, and that may not be able to reach all the way at the end. But that'll be one of the 2 different things that could happen. And yeah, that's that. Alrighty, let me see if I can get this focused a little bit. Okay. So compare and contrast the sympathetic division of the ANS, the parasympathetic division, and the somatic nervous system. So first, I'm going to just draw the, real quick, this is, alright. So we actually have our nervous system up top, which is split into 2 different things, central nervous system and our peripheral nervous system. Central nervous system splits into 2 things here, your brain and your spinal cord. Your peripheral nervous system splits off into autonomic, and somatic. Somatic breaks off into sensory and odor. Autonomic then goes off into parasympathetic and sympathetic. So this is the nervous system. So compare and contrast the division. So we're going to compare and contrast this thing down here, parasympathetic, sympathetic, and just somatic. So they're points of CNS origin. So CNS origin. For our somatic system, no, let's do our sympathetic first. So this one's going to be in your spinal cord, and it's going to be like T1 to L2. So it's going to be a big chunk of your spinal cord. It's going to be where the sympathetic nervous system starts, where its origin from the CNS is. So let's just write T1 to L2. And this will be sympathetic. And then for parasympathetic, so sympathetic, parasympathetic, and somatic. For parasympathetic, it is like your brain stem, and also, I forgot what it's called. I don't remember what it's called, but it's like the very bottom of your spinal cord. I'm pretty sure it's like S2 through 4. I don't remember what it's called down there, but that's where your parasympathetic comes from, the nervous system. And your somatic is going to be the ventral horn of your spinal cord. All right. What else do we have? Their origin, number of neurons. So sympathetic and parasympathetic are both a 2-neuron system, meaning they have a oh my gosh, I'm gonna screw the word up. Ganglionic. Sorry, that's okay. ganglionic, preganglionic, and a post. But our somatic system really is just a one neuron system. The location of ganglia. So our somatic doesn't have any because it's a one neuron system, so it won't have any. For our sympathetic, it's going to be closer to the spinal cord. I don't know where to write that, but sympathetic. So let's do, what am I doing? Ganglia? Location. So for sympathetic, it's going to be, gosh, I can't draw. For sympathetic, it's going to be near spinal cord. And for parasympathetic, it is going to be near the target organ. Or I guess like destination of where those neurons are going. The neurotransmitters. So for our sympathetic, we're going to have the ganglionic. Let's just cross right here. We'll do sympathetic and para. We're going to go right here. This is going to be the post. So for this one is going to give off ACH, but it's post-ganglionic is going to give off norepinephrine. But for our parasympathetic system, it's going to give off ACH for both pre and post-ganglionic. And then, I didn't do the somatic. So the somatic is just going to give off ACH as well for the skeletal muscles. I don't know where to put that, but we'll give off ACH, and that'll be for the neuroskeletal junctions and for its skeletal muscles. The types of receptors and the actions of the receptors. So for sympathetic, we'll do receptors here. For sympathetic, para, and somatic. Soma. Sim, para, soma. For sympathetic here, can you see that? Yeah, you can. Okay. For sympathetic, we're adrenergic. It has adrenergic receptors. For parasympathetic, it has muscarinic. And then for somatic, it has nicotinic receptors. And then the actions. I just stepped on a cord here for church. I hope I didn't break that. So is that the actions of the receptors? Let me see. Okay. Actions. So for adrenergic, it's going to want to depolarize the cell. For muscarinic, it's either going to depolarize or hyperpolarize the cell, or the post-ganglionic neuron. Sorry, not cell, but the post-ganglionic. It's going to want to depolarize. This one, it's either going to want to depolarize or hyperpolarize. And then for nicotinic, it's just going to want to stimulate or inhibit the target organ. There we go. Okay, so discuss cholinergic and adrenergic receptors. All right. I'm running out of room. But that's okay. So let's see. Let's erase, I guess just this. We'll erase right here. So I can keep going. Honestly, I don't even need this up here anymore either, but that's fine. So discuss cholinergic and adrenergic receptors. Cholinergic, oh, spelled that wrong. Adrenergic. So cholinergic is going to bind to ACH, while adrenergic is going to bind to catecholamines. So cholinergic receptors want ACH to bind to it, but adrenergic is going to get what did I just say? I'm sorry, I'm blanking. Catecholamines, that's what. Catecholamines. How I sort of think of it is, when I just think of the two, I think, okay, well, one will give off catecholamines and another one gives off ACH. And for adrenergic, it sort of sounds like adrenal or adrenaline. And what gives off adrenaline is going to be some of the catecholamines in the neurotransmitters. So yeah. Explain the different subdivisions of each type. Okay, so for cholinergic, we have, this is the one that has muscarinic. Oh, I should have. Here we go. We have muscarinic and nicotinic. I guess I should put this instead. So for muscarinic, that is going to what's the word I'm looking for? Parasympathetic. This is going to be on close to parasympathetic, sympathetic target organs. So these receptors are going to be at the end of a ganglionic. It's going to be on a post-ganglionic neuron in the parasympathetic system, close to the target organs, because it wants the ACH to bind to it. That way it can give off the neurotransmitters that it needs for the wait, did I say that right? I don't remember if I said that right now. Now I'm second guessing myself, but I'm pretty sure that's right. I wanted to pause it, but I don't know how to splice these things perfectly, and so I'm going to leave it as is. And for the person that's grading this, I'm so sorry. That was a little bit of a losing my mind, but I've been doing all these in the past like 3 days, so I'm sorry. But nicotinic is another cholinergic receptor, nicotinic. And so that is going to be in the autonomic ganglia. Autonomic ganglia. And it's going to be trying to target like smooth muscles and blood vessels. Smooth muscles and blood vessels. It's also, I'm glad I thought of this. It's also going to be neuromuscular junctions. because nicotinic receptors are going to be part of the somatic system. And this will be, since it's a one neuron system, and it's not binding with, it doesn't have a pre or a post ganglia, it's going to go at the end of the neuron, and it's going to be right at the junction where the neuron then hits muscular or skeletal muscle. And so this will be to, this is what helps us actually move muscles, have voluntary movement, is going to be all of the nicotinic receptors charging off and telling us to move the muscles in the skeletal muscular, I guess it's the neuromuscular junctions. There's that. And then we have adrenergic. I keep feeling like I'm spelling it wrong. Is it a D or a G? Adrenergic, right? No, it's a D. Adrenergic. Adrenal. Adrenergic. So these receptors, or actually this is a subdivision. These are just going to have alpha and beta. Alpha receptors and beta receptors. And alpha is going to be more for like blood vessels, smooth muscle, blood vessels, smooth muscle. And beta is going to be more towards like your heart, your lungs. I think there's one more I missed, just like organs in general. So yeah, there's the subdivisions of the receptors. Give mechanisms of action for each type of receptor. What happens when the neurotransmitter binds to the receptor? So I think I sort of said this earlier here, actually. When a neurotransmitter binds to an adrenergic receptor, it's going to want to, wait, that sort of sounds wrong. For nicotinic, it's going to want to depolarize. For adrenergic, it's going to want to stimulate. I think I wrote that backwards, but this is actually it, like right here. So I'll just redo it. So when a neurotransmitter binds to a certain receptor, so we're going to do, we'll do muscarinic here. And when muscarinic gets bound by a neurotransmitter, it will want to either depolarize or hyperpolarize. De or hyperpolarize. For nicotinic, it is going to want to depolarize, because if it wants to depolarize, then it's going to have this action potential, and that's what it's going to want to do, is cause an action potential. So it's going to want to depolarize. And then for adrenergic, this one is just going to either stimulate or inhibit the target organ. And that is what happens when the neurotransmitters bind to specific receptors. Now I'm going to I'm trying to think, where did I go wrong on this? I don't remember. I feel like I just erased something that was like a little backwards, and I feel like in my head it made sense. Discuss the receptor and then show what happens when they get I don't know. But we're going to leave it at that. I'm pretty sure I answered all the questions. So yeah, sweet.